So far we have discussed examples of reactions which are actually irreversible in nature. Something like I said that if you remember the very first example which we took, we wrote it like this. It's irreversible in nature. Now what happens if the reaction is reversible? In principle, all reactions are reversible in nature. You can actually see irreversibility under certain conditions if the back reaction, which is the reverse reaction, is too slow, or kinetically, which means actually kinetically forbidden reaction. So then in that case you can see the irreversibility. Otherwise, most of the chemical reactions which you studied in high school, a statement that chemical reactions are reversible in nature. And what happens, you also understood, you also studied there, that if you start a reaction, sooner or later an equilibrium is attained. Now we'll just talk about this equilibrium thing, how the equilibrium is attained. Now let me start with a very simple example. Suppose A is going to B and B is also giving back you A, and the stoichiometry we are just taking here to be 1:1 just to avoid the complications, but it's not too complicated because you can always absorb the stoichiometry into your rate constant and redefine a new rate constant. Now suppose for the forward reaction I say that the rate constant is K1. For the reverse reaction I'm just writing it as K minus 1. Some textbook actually use for forward reaction a notation like Ka, and reverse reaction they write it as Kb, something like that, or sometimes they write it as K1 for the forward reaction and K2 for the reverse reaction. Some textbook write Kf, F for forward, and Kb, B for backward, something like that. So I'm just using 1 and -1 notation. -1 means it's at the opposite direction. Opposite in the sense that which we have chosen, like A to B by our definition, by our choice, is the forward direction. Now we can actually solve again in the similar way, and then the integrated rate law looks like something like this. I'll just describe what are the results, how the concentration of A or B actually changes with respect to time following this integrated rate law. Now suppose we started with an initial concentration of A, which was A0, and then the rate law will look like this. Again, the derivation may be found in any standard text. Either the text might have the solution itself in the discussion, or it might have it as a problem set which you have to solve, or you can actually go back and look at the YouTube video lectures on Introduction to Chemical Thermodynamics course. Now look at it carefully. We can actually write it either in the logarithm form, or we could write it in the exponential form like A minus A equilibrium is basically A0 minus A equilibrium times exponential minus K1 plus K minus 1 into T. Now here the question is what is A equilibrium? So A equilibrium is the equilibrium concentration of A. Now let us try to understand how the plots will look like if I want to plot, say, A versus T, or the concentration of A, how it is varying with respect to time following this equation. Now as I know that initial concentration was A0, we can quickly check if I put T equal to 0 in this equation. So this e to the power factor that goes to 1. So I have basically A minus A equilibrium is basically A0 minus A equilibrium. So A is nothing but A0. So that makes sense. And with respect to time, what I see here is that the concentration actually drops, but it drops exponentially, of course, just like a first order reaction. But the rate constant is not just K1, it is actually K1 plus K minus 1. So the reverse reaction also contributes. And before that, let us just try to understand what is the final concentration of this thing. Now for that I can actually think that when T goes to infinity, So this entire thing becomes 0. So by solving, we'll see that A will be equal to A equilibrium. So at a very long time, actually it reaches the equilibrium concentration. Suppose A equilibrium is somewhere here. Now A equilibrium is a constant. If we do not change the temperature, so A equilibrium will be constant. So what we just learned is that eventually the concentration will drop, but it will not drop to 0. It will just reach the equilibrium concentration of A, and the curve will look like something like this. So it will be an exponential decay and reaching exponentially to this asymptotic value, where this decay is actually exponential, but it goes as e to the power minus k1 plus k minus 1 into t, and which is very important. Similarly, for the B expression also, we can have a similar expression like A, and B will also reach its equilibrium concentration. And suppose B equilibrium is somewhere here. And if we start, or if we assume that initially the B was at 0, so then we'll see that the B also reaches with the same time constant to its equilibrium value. So this will also be something like 1 minus e to the power minus k1 plus k minus 1 t. It is an exponential growth, but the time constants will be same. So the point here is that for an equilibrium reaction with two rate constants, two opposing rate constants, k1 and k minus 1, you will see that the way it reaches the equilibrium, it doesn't depend only on the forward rate constant or the reverse rate constant. It actually depends on the summation of these rate constants. And so in this plot, actually we plotted either the concentration of A or the concentration of B. So this is a general plot. Now interesting thing to look here is that we assumed here that the B equilibrium is greater than A equilibrium. At a very long time, the equilibrium concentration of B is higher than the equilibrium concentration of A. It need not be the situation, it may be reversed, and in those cases the B equilibrium will lie lower than the A equilibrium. So the curves will look like something like this. This is for A and this is for B. So the amount of the product in this case at a very long time, when t goes to infinity, in the long time limit, is actually constant, and you can actually see the ratio can be connected to the equilibrium ratio of B and A, and which is nothing but your equilibrium constant, which is the thermodynamic equilibrium constant. Now we have to be very careful when we say thermodynamic equilibrium constant, because strictly by definition, whenever you write a thermodynamic equilibrium constant, it is unitless. So all these B's and A's are actually inherently, we have to assume that it is divided by the unit concentration. Like if I express say B in terms of moles per liter, I have to divide by 1 mole per liter, or the standard concentration unit, so that the K equilibrium becomes concentrationless. In this case, we took 1:1 stoichiometry, so naturally the concentration it is unitless, but it may be so that the reaction can have say the equilibrium constant expression can have B squared divided by A. In that case, to make it unitless, we have to first divide B by the equilibrium unit concentration and then take the square, so that everything becomes unitless. Now as you see that in this case, the A and the B, either of them, or I mean both of them, basically approach their individual equilibrium concentration. It is not going to 0, or the entire A is not going to the B, which means the B is basically not going to the initial concentration of A, which is opposite to the first order reaction. And that's the importance of the equilibrium. So equilibrium suggests, ensures that everything actually reaches finally to its equilibrium concentration. I will give you another example of a different type of reaction, where it is known as opposing reaction. So where a single reactant A is giving you two different products. So I can actually call this rate constant as say K1, and this rate constant, let's say, as K2. And in this case, now the integration of A is very straightforward because it's just a first order in A. It's a first order process giving rise to B. It's also another first order process which is giving rise to C. So the integration for the rate equation for A is pretty straightforward. It will be minus K1 plus K2 into T. Now what about B? Now in the same way we can actually solve the integrated rate law for B, and you will find that it will be something like K1 by K1 plus K2 into A0 into e to the power minus with respect to time both the B and the C will grow. So any exponential growth we can actually show it like 1 minus e to the power minus K1 plus K2 into T, and similarly the concentration of the C will vary. Instead of K1 here I will have K2 in the denominator, and everything else is just like the equation for B. So the assumption or the initial condition was that only A was present, and the concentration at time 0 for A was A0, and concentration at time 0 for B and C was 0. Now if I plot these concentration A, B or C, A or B or say C versus time, now the profile for A is pretty straightforward. It will have a exponential decay and it will go to 0, of course, because it's all irreversible reaction. And but remember that it falls with a time constant which is not K1 or K2, it is actually K1 plus K2. Now B and C will grow, and eventually as you can see, if I make this time to be infinity, so this part actually goes to 0. So what we will have is basically A0, the initial concentration, times some factor which is K2 by K1 plus K2 in case of C, or K1 by K1 by plus K2 in case of B. So we will have exponential growth, and the final concentrations will be something like this. Let's say this is the curve for B and this is the curve for C. Now what we see is that at a very long time, the ratio of B by C is nothing but K1 by K2. So what it means is that the ratio of the B and C in the long time is dependent on the rates of how they were formed. So this type of products are known as kinetically controlled product, meaning the kinetics or the rates are actually controlling the absolute value of B and C in the long time limit. Now we can actually see the beauty once we actually impose the condition that these reactions did not happen as a irreversible reaction, but rather they had a reversibility. In the sense, all I'm going to do is, instead of writing it like A is going to B and C irreversibly, now I'm imposing the condition B also gives back to A and C also gives back to A. So I can actually think about the rate constant as K1 and K minus 1, and for the A to C reaction and vice versa, I can say the rate constant K2 and K minus 2. Now we have already studied what happens for equilibrium. Now considering AB equilibrium, we know that in the long time the ratio is the ratio of the products will be nothing but B equilibrium by A equilibrium, which is related to the equilibrium constant, which is also related to their ratio of the rate constants. And similarly, we are discussing when it's a very long time where the equilibrium has reached. Similarly, for this equilibrium A to C, we can also say that the long time ratio will be dictated by something like this, which is the equilibrium, it's just for the second equilibrium, and we can also write it as the ratio of the individual rate constant. we can actually ask this question, what will be the final ratio of C and B? We can just take the ratio using these two equations which we have written here, and then we'll find a beautiful thing that it is basically ratio of the equilibrium constants, which is nothing but K2 by K minus 2 divided by K1 by K minus 1. Now you see that it is not simply K2 by K1 as we just saw earlier, where actually did not consider any reversibility, and here. So now the back reactions are also important, and it may so happen that although in this case I have B is higher than C because K1 is higher than K2, it might so happen that this thing, the overall thing, may be positive, meaning although K1 is greater than K2, the overall thing K2 by K minus 2 and K1 by K minus 1 may adjust themselves in such a way that they can be more than 1. In that case, actually in the long time, C will dominate. Now if I want to plot it, this situation, it will be something like this. A will be always exponentially decaying, and B initially will be forming at a higher rate than C, but then eventually what will happen is that the C will reach its equilibrium concentration, whereas the B concentration will be lower. So this is basically C equilibrium, and this is suppose B equilibrium. So we see that at time at a early time, it may so happen that we are only forming, suppose we start only from A, and then you are forming B in one channel and you are forming C in the another channel. Now then, as soon as the B forms, after a certain time, the reverse reaction rate also increases, because you remember that the rate is nothing but rate constant times the concentration. So initially, if there is no B or C, only the K1 and K2 will dominate, only the forward processes, this rate and this rate will dominate. But later, when in the reaction mixture we have sufficient amount of B and C, then the reverse reactions also proceed, and then you can have a situation that the entire thing might change. So the equilibrium ratios might be very different. So in this case, we say that these products are thermodynamically controlled, because everything is dictated by the ratio of the equilibrium constant. If it is a higher equilibrium constant, that product will be formed. Now we can cast this entire thing in the energy level diagram. Now what is an energy level diagram? All of you know that the rate constant is connected by Arrhenius equation, which says that for any rate constant, I will have some energy which is known as activation energy, which is kind of an experimentally determined quantity and which can be connected to the minimum energy that is required for a reaction to happen. Now for any reaction, say A to B, we can say that there is an activation energy, in the sense that suppose this is the energy of the A, okay, and this is suppose the energy of the product B. Now this does not happen, although energetically B is more favorable. By energy we always mean the Gibbs free energy for the reaction, and we say here that A to B, there is an activation barrier, in the sense that you have to cross certain amount of energy, you have to supply certain amount of energy for the reaction to happen. In this case, this is the activation energy for A to B. Similarly, when B actually forms, it also has an activation energy, which is activation energy for the reverse reaction. Now what we have said that in the earlier example of kinetically controlled product is that at a very early time, what is happening is something like this. I had A here, and then I was forming both B and C. Suppose B had an activation energy which is something like this much amount, but C had an activation energy which is much higher. Okay. So as you can see that the activation energy for this reaction A to C is much higher, which means actually the rate will be much slow, because if you remember that rate constant is actually proportional to minus e to the power minus Ea by RT, where if I have a higher activation energy or higher Ea, will have actually less amount of the rate constant, or the value of the rate constant will be less. So what it means is that the kinetics or the activation barrier is controlling the product ratio. However, it may so happen that in a longer time, as the B accumulates, the reverse reaction also happens, and initially suppose going from A to C had a very high barrier, but then thermodynamically C is more stable than B, the way I have drawn here. As you can see, in the free energy diagram, the position of C, or the free energy for the product C, product C is much more stable than the product B. So what we can say here is that as soon as initially, so everything is dictated by the activation energy for the forward reactions. In this case, the activation energy for going for A to B is smaller, so B will form more, as we can see at this up to this time, which is shown as the dotted line here. So the B is actually lying higher than C. But as time progresses, the reverse reaction also takes place, and what happens ultimately at the end of the day, everything is dictated by the ratio of the equilibrium constants, and that will be dictated how the product is thermodynamically stable. In this case, since C is stable more than B, we expect the long time concentration for C, or the equilibrium concentration of C, will be more than B. Also, a point to note here is that if you see it carefully, for the reverse reaction B to A and C to A, the way I have drawn it, since actually C is much more stable, it is actually lying much below in the energy level diagram, energy scale, than B. Now, which means actually the reverse reaction activation energy from C to A is much higher. So C to A will be much smaller. So which means actually this K minus 2 will be very small. So which actually makes this overall ratio much more than 1, so that C equilibrium is greater than B equilibrium. So, so this kind of diagram is very important to understand how basically in a short time scale we can have, when the reactions are, I mean, you can approximate it as a irreversible reaction, a irreversible opposing reaction, that A is going to B and A is going to C, and then moment you add or impose the condition that B and C can also come back to give you back the product A, then you see the beauty that everything is now reach equilibrium, and the equilibrium, at equilibrium the concentrations will be solely dependent on their equilibrium constants, which are actually combination of all these forward and reverse rate constant. There are 4 rate constants, and so let me summarize this part. So far whatever we just explained, irreversible reaction, A plus B is going to product, something like that. And then eventually we said that, okay, instead of irreversibility, what happens if we just include reversibility of the reactions, and we saw that how the ratios actually reach the equilibrium concentrations. Then we said that what will happen if we have 2 competing channels in the reaction, and we showed that initially everything will be governed by the rate constants or the kinetics, which are connected to the activation barrier. So the smaller activation barrier will have the higher rate constant, and that product will be favored. But eventually with time, as B and C gets accumulated, the reverse reaction will also happen, and then everything will be dictated as the ratio of the equilibrium concentration will be dictated how thermodynamically they are stable. And the example which we gave, remember that the way we showed it is that the kinetically controlled product, which is B, is not thermodynamically controlled product, which is C, and that's why the traces actually reverse. Initially B was higher, but eventually the C takes off. And for this other case, you can also have a situation where one of the products, let's say C, is both kinetically and thermodynamically favored. In that case, when I am going from A to say C, the activation barrier is smaller, as well as C is much more stable. When I am going to A to B, the activation barrier is higher, as well as B is thermodynamically less stable than C. As you can see, the position of C is much at the bottom, and also the activation barrier for going from A to C is smaller than going from B to A to B. So in this case, C is both kinetically as well as thermodynamically controlled product, meaning from the very beginning you will see the C to be formed. In the next part, we'll consider another class of interstring reactions, which are known as consecutive reaction, which is something like A is giving a intermediate which is B, and B is subsequently giving an intermediate C, and we will consider all these consecutive reactions are very important, so we'll consider it in some detail. Again, we will not solve the equations which are integrated rate equations. You can always go back and look at the standard text or the YouTube videos of the preceding course.